you. Our last speaker of this session is David Hiner from Amkor. David joined Amkor in 1997 and has held various management positions in quality, substrate technology, and advanced interconnect and wafer level package development. He's worked in the assembly and packaging industry for more than 30 years, holding positions in product and package development at Surfect Technologies and RF Micro Devices. David has been issued 22 patents in semiconductor packaging, holds a BS degree in chemical engineering from Arizona State, and an MBA from the University of Phoenix. He's going to talk to us about chiplets, building blocks, and future packaging trends. David, all yours.
Thank you very much, Robbie, for the great introduction, and thanks to the MEPTEC team for getting Amkor in somewhat on short notice onto this track today. I'll quickly cover, this is my agenda, so I've got some high-level trends, sort of, directing the chiplet technology. I will attempt to answer again, as everyone has, the age-old question of what is a chiplet. I'll then go in a little bit to the motivations from the OSAT perspective, at least from Amkor's perspective, what's motivating, a large sort of swath of customers as they move towards chiplets. And then, the second half of the presentation will really get into the different packaging technologies that Amkor is deploying to sort of support all these different chiplet, what we consider to be chiplet products. And, it's very diverse, and I think that's where a majority of maybe some of the questions will come from. So I will stop sort of in between, Ravi, probably after the chiplet motivation for some early questions, and then we can kind of wrap up at the end with some other questions. As far as market drivers, the high performance and product packaging trends, are really broken into what we consider to be four buckets. There's the need for higher memory bandwidth at lower power. And this is the co-packaging of memory, either within the package or, even on chip. There's this high wafer cost, higher IO count driver. There's also a couple of power related drivers, the power delivery network, and then just getting rid of the heat, dissipating the power through improved thermal dissipation. But it's really in the high wafer costs and higher IO count that really is the main driver we see for chiplets. And it's this idea, it's been around for years. I think it's really now finally coming to the forefront, and that's this, sparingly using the most current wafer node where the wafer costs are most expensive, and then, using a low, a older node for as much as you can. And so, that's the main driver. So as far as what are chiplets, this is our kind of descriptor, where you've got over here on the left an example of one of AMD's SoCs, and the idea of breaking this SoC up into its functional blocks, and then repackaging them or reconstituting those functional blocks into chiplets, and then those chiplets essentially are placed in a package next to each other. And those different packages, there's a wide variety of what those packages may be, but that's essentially our view of chiplets as to what it is. As far as why chiplets, I spoke, there was that slide earlier on cost, and this graph here kind of shows some of the historically normalized costs for different nodes, going all the way back to 45 nanometer, all the way up to where we see 5 nanometer landing in terms of normalized costs for a yielded square millimeter. And this is driving, we believe, the push for chiplets, but at the same time, the packaging or the final system has to be of the same or greater performance. So you can't go to lower costs without maintaining performance. And so those kind of go hand in hand. We see performance being maintained, and in some cases, we believe performance will be improved in the use of chiplets. So from the SoC to chiplets, there are different paths depending upon the end user or the end product. So in this case, we've got three sort of categories blocked off. We've got the data center, we've got notebook computers. These are more mobile computers. And then we've got the more high performance, faster 5G processors. This could be GPUs, maybe some other high end CPUs. And essentially at the top up in the data center, this is where products like, for instance, AMD's, their current products are packaged essentially a CPU surrounded by IO die just on a substrate. And so this is where we are today. These are lower IO communication between the main ASIC die, CPU in this case, and these IO chiplets. Now, these IO chiplets they could be SerDes, they could be PCIe, they could be memory IO. There's some customers looking at voltage regulator modules that could be packaged on the substrate just in an MCM. And so this is just many die placements on a traditional substrate. Now down where the IO gets more dense, this is the IO between one chiplet and the ASIC. We see the need to integrate with a higher performance, like a module base. So that this blue shaded area represents essentially the module. And in that case, you could use 2.5D, but most customers are targeting this HDFO, this high density fan out. Amkor calls ours Swift, but everybody has a different name essentially for this organic RDL with the die attached to it, and then that module being attached to the substrate. As far as the die-to-die interface, I won't spend a whole lot of time on this, but whether the chiplets are packaged in an MCM or in a module oftentimes comes back to how the die are communicating between each other. So in the case of a parallel interface where there's a lot more physical wires and lower latency and lower power, we see the need for that module and the higher routing density that those modules can provide. So whether that's a silicon interposer or a high density fan out solution, really depends upon the customer's needs. As far as serial interfaces, this is your more, again, going back to that traditional case where lots of different chiplets are being packaged just on a substrate. Those have fewer physical wires, but drive, much higher power and higher latency. So we see, these two scenarios tying into these two different sort of cases for chiplets today. This slide kind of goes, does a deeper dive into those drivers. On the far left, you'll see, a variety of some of the drivers that are pushing people towards heterogeneous integration and chiplets, starting with the wafer cost, which I've already highlighted, but there's also design costs. And so, the customers designing for instance, an IO die could save design costs by designing that IO die and then reusing it across, say, multiple product offerings. There's also this need to manage power. There's an IP reuse, so a customer may certify an IP block and be able to then reuse that without having to recertify it again and again at different nodes. So there's a big push for that. This time to market, also, if you can imagine being able to reuse devices that you may have designed in a previous node, you can shorten the time to market for that aspect of the product. So impacting all of these different areas that you see on the right, all of these face the need for better power dissipation and better power delivery networks. So these are kind of common along with the items on the left. But when you get down into the actual products, these, we've kind of put them into four main categories on this slide. And that is in the deep learning AI space, we see the primary driver being memory bandwidth, and on sort of over to the right, you'll see the memory all being kind of co-packaged in a module that could be in a 2.5D, it could be in an HDFO. Low power also important, but memory bandwidth is the primary driver for chiplets here in the deep learning and AI space. As far as networking, we see really it's an increase in IO count, more gates, everything going faster basically. And that's sort of a mixture of packaging the IO with the ASIC and in addition, the modular approach where the IO and the memory are sort of packaged together in a module form that you see over there to the far right here. I mean, you can see my pointer. In the CPU server space, you'll see most of it's really just MCM. So these would be IO die surrounding one or more potentially ASIC or CPU dies. Could this eventually move to module? Sure. Really, really depends upon what sort of chiplets are trying to be sort of integrated together. And then finally, in this sort of bottom category, this is almost like a chiplet within a chiplet. It's hard to describe, but these modules here that you'll see in this sort of GPU space could be, they're smaller in some cases. They're, it's sort of this differentiation of larger. There's part of the industry it's moving towards larger, and there's another push in terms of chiplets that sort of are moving smaller. It's hard to imagine that, but there is some interest in a smaller size as well. So this slide, this will be my last slide before I take some questions midpoint, but we've got basically three kind of packaging solutions that we're using to sort of support the chiplet integration at Amkor. And this first one on the left is just your traditional substrates to start with, this MCM. This is where we're packaging perhaps a single ASIC, maybe more than one ASIC, and several multiple IO die, as in this sort of cartoon diagram here, you'll see. We are also working on some added versions of the MCM where we've got a more traditional, a lower tech substrate, perhaps down here, maybe a HDI type substrate. And on top of it sits a more advanced substrate. And those chiplets could be packaged on either of the two tiers. So you could have some on the lower tech substrate with the CPU and other chiplets packaged on the upper substrate. Again, it's in development, lots of activity in this space. In addition, on the substrate, there are some hybrid substrate technologies that Amkor is working in a pathfinding environment on. This could be a sort of substrate made out of RDL and mold, like you've seen in this sort of cartoon. But there's also some glass core technologies, some advanced RDL on glass that we're also working on.
What's the difference between POP and Pathfinding and Swift 3D in development?
Yeah, that's a good question. So we did so I think this one on the right, this one over here is really I know it shows two die here. We've done it. We did work in the past where this package was developed with a single die here and a single die up on top. And so this pathfinding is essentially the idea of of multiple top die.
Got it.
Yeah.
Okay. Then there's a question that says on slide 9, I couldn't get the die partitioning impact towards many equal dies reconnected on an interposer. Could you comment on that?
Couldn't get the.
I don't also, to be fully honest, I don't fully understand the question.
Yeah.
I suspect the question is why are you partitioning and reconnecting on an interposer?
It's all about the routing requirements of the customer. Amkor doesn't make our own products, right? So we we service our customers, and so our customers, may require a particular routing density, and we some of those routing densities can only be satisfied on a, say, a 2.5D interposer today. So
Correct.
sub micron, routing is really only possible on a silicon interposer today.
Right. No, there's clarification here. It says, for example, the AMD EPIC line for
Uh,
server CPU. So I think it is interposer versus traditional organic interposer. That's
Yeah, I think most of that, and I'm not an expert on that particular package, but I believe it's all basically similar to this. I don't know if you can see my cursor, but it's CPU with chiplets surrounding it, just on a substrate, like an MCM, like a this sort of format here,
got it.
where it's just a lidded flip chip BGA, but with advanced rules for placement and underfill.
Two other questions have come up. One is, can you
Mm-hmm.
comment on this one? It's bread and butter for you. Can you
Yeah.
comment on thermal and warpage issues?
It depends. So that there's so many different versions that you see here. The thermals for, say, the MCM are, there is a lot of needs, as I alluded earlier. There's a thermal driver for basically everything going forward is generating too much heat, right? So there's a need to enable this sort of chiplet path for some of our advanced thermal solutions, including metal TIMs. And so, the thermal solution for a basic MCM is pretty straightforward. But if you start, looking at thermal solutions for, say, these 3D applications, or some of like this stacked MCM, the thermal, how you lid or how you thermally sync these different tiers, certainly is an added challenge to the package structure. Yeah.
Got it. And then one more question. Where do you usually put the thermal interface materials and the heat spreader in a package? What happens in chiplets?
Um, yeah, very similar to my last answer. So again, we try to utilize more of a industry standard lidding approach. Some customers use like an active, like a they attach the active thermal solution after Amkor is done. So some of it is basically a stiffener ring with an exposed die, and then the customer will attach a vapor chamber type cooler with a fan to cool the like a CPU. And in other cases, there might be, in the mobile environment, there might be a flat top lid. There might be a like these lids you see here, this sort of formed heat spreader that you'll see on, say, like most of the AMD CPUs are all, and Intel, they're lidded, right? Everything is a lidded.
Yeah,
There's a TIM applied to the top of the die at Amkor, and then the lid is attached, typically through snap cure. Yeah.
got it. Thank you.
Mm-hmm.
If you tell us what the RDL on glass is targeted for, what's the benefit of glass? Is it just a carrier?
So Amkor does a lot of our RDL fabrication for what we call Swift here, HDFO, on a glass carrier. So we use glass, but not as a permanent element of the package in a lot of these methods on the far right. Now, in terms of the hybrid substrate, there are some, like, through glass via technologies where the glass becomes a permanent element, and a lot of that is truly pathfinding, and so I can't really comment on that at this point. But we use glass only as a carrier in the Amkor HDFO fabrication process. Yeah.
Sounds fair. Dave, I'll let you continue and finish
Yeah,
your
yeah,
piece.
yeah. I'll try to be quick. So these next few slides kind of delve into the details of the different packaging solutions. So quickly on the MCM, I'm just giving you guys a taste of some of the new stuff that we've worked on as far as MCM goes. This particular test vehicle, we took a very large die size. This is all an Amkor, so there's no electrical connections that are tested, but we were really testing, could we do the assembly. So we took this large die. We then took a couple of cuts at creating chiplets, essentially, and we placed these die in this orientation next to a smaller, say, simulated ASIC with a set. All the gaps between the die, these dies were at 70 microns. And you can kind of see the two configurations, and just showing some SAT imagery after 1,000 cycles at TCB. We found no abnormalities. So we were able to underfill two different ways. We were able to underfill on the right. We dispensed essentially along this long end on the right, and the underfill is literally, flowed across the large die and then under all of the small MCM die without issue. In the case on the left, we dispensed along each individual chiplet got a dispense of its own, and that one also had no abnormalities. So the ability to extend the capability of traditional MCM for this sort of underfill shows good promise. So completed some feasibility, and essentially we're in a position now where we're customer prototyping this sort of traditional substrate MCM, but with high density die placements. Okay, so as far as HDFO, this is our RDL on, our RDL fabricated at Amkor. I think the most important thing here is that diversification that I spoke to a little bit earlier, where we see both a push for lower cost, which is lower layer count and kind of less, one or two die, and it may be a die first or a die last approach. So we have a couple of approaches at Amkor where we do both a die first and a die last. And then we also see a push for these really huge, like in this sort of cartoon where there's, there might be 8 HBM and 2 large ASICs all in one really big, larger than reticle sized module. We are moving to 6 layers. I won't spend a lot of time on this slide. You'll be able to see it in the when the slides are shared out. But we've done a lot of work up to 4 layers, but we're moving on to 6 layer for our Swift HDFO RDL process. This just shows some of the joint analysis at TCG 1000 for the HBM joints for what we call substrate Swift. And then finally, sort of a status. Right now we're basically internally qualified for 4 layers of 2.2, and we're moving this year to 6 layers with some product quals targeting 2022. And then the larger than reticle size, really large modules are sort of, a little further out there. And so we have development that's ongoing. Just quickly, I think as Jan, mentioned, Amkor does have a bridge technology where we can embed either a silicon bridge. Amkor has a molded bridge that we've been working on. We can embed whether they're IPDs or actives or passives as well in this same process. And so this sort of extends our HDFO or Amkor substrate Swift technology through the use of these tall pillars that you see in this sort of diagram. These tall copper pillars enable the embedding of these components under the die. It's kind of a picture of it. I won't go through a lot of detail on that because I know I'm probably already out of time. Just quickly on ultra fine pitch, it's also been talked about. So Amkor today in production at 45 micron pitch with all of these. This is mass free flow, thermal compression bonding, and laser assisted bonding. We have validated all the way down to, I think, to 18 microns with mass free flow on chip on wafer. And we're in some feasibility testing down to 10 micron pitch with mass free flow. Again, thermal compression and laser assisted. And then we are pathfinding on hybrid. Really, we're trying to find a a alpha customer to help us with the, to move forward on copper. It's a very complicated thing for an OSAT to enable without understanding the customer input directly. So that's it for me. I'm sure there's more questions if we
David,
have
first,
time.
yeah, no, first of all, thank you. This is excellent. The one question we had, there's two questions. One was, what was the minimum bump pitch used in your test vehicles? I think you answered it in the previous slide. Yeah, one before.
I assume it's on this one up here, perhaps. This guy. I think this is the 45. I believe that I kind of highlight here at the end. I don't know specifically, but my understanding it's probably a mixed bump pitch, but
Right.
I believe the minimum in that test vehicle is 45.
Okay. And then there are two other questions. First is, what is the minimum via and pad size dimension in Swift?
Minimum via. I don't know that I can go into the specific details. Via sizes, I know it really depends upon the dielectric thickness. So the thickness of the dielectric layers impacts the via size. I think we've gone down to 10 microns, and I think the pad size is it's variable between. I'm trying to think if it's 20, might be around 20. I'd probably need to take that one offline if someone really wants to know those rules.
Yep.
Yeah.
And then last question, what is the fine pitch probe limit these days? Like, what is the pitch limit to fine pitch probe?
Oh, for test.
Test,
Yeah.
yeah.
I don't know if I know that one right off the top. I know we're able to probe that 45 micron, down near 40 micron we can probe, but the probe cards are pricey. They're a lot of money to probe down to that pitch, as you probably know. And so I don't know that we've gone below that. I know there's a lot of people working on being able to probe down to 30 micron pitch. So it's really, how do you probe and not damage the
Surface.
surface, right?
Yeah, yeah,
So
absolutely.
and we have done some work on probing pillars. So where we don't actually probe the wafer, we plate the pillar and probe and then reflow the pillars. So we have done some work there.
Got it. Okay, I'll turn it over to Ira. I think we've answered all
There's
the questions.
one last question in the chat. Sorry,
Oh, okay.
from Jan again.
Yeah.
Okay. Jan has a comment that says, Intel presented an ECTC paper that there's a limit to assembly with micro bumps around 20 micron pitch. Is your 10 micron pitch only with laser assisted bond?
Number one, Jan, it's not to substrate. So this would be like chip to wafer. I do believe that most of that is probably not mass reflow capable. I think at this time Amkor's doing feasibility, so I don't think we're in a position to say that we can do mass reflow, but we are trying, and probably it's going to be lab, or it's going to be laser assisted or thermocompression, but we always are trying to push the limits. Yeah.
Fair. I think now I can turn it over to you, Ira.
So once again, thank our sponsors, Advantest, Amkor, and Synopsys, who made this event possible. Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Amkor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys, with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.